strength of materials and structures. And we're doing module 3, which is temperature stresses. Okay, so I'm just going to give you a small lecture. I don't want to spend more than 10 minutes on this because we need to solve problems. I'm going to copy something and I'm going to talk. Okay, so that's a problem we're going to solve. So guys, I did mention to you, right? We're looking at the 5 fundamental mechanical loads. We've done some analysis on tension, I believe. I believe you did that. Tablet is out. Right, we did some analysis on compression, I think. You did look at that and you had a look at shear, right? For the rest of the other 2 modules, you also, the next module we'll look is module 7, which will be torsion, the twisting force, and eventually we're looking at bending. But what is not shared here is 2 other mechanical loads, right? And here are they as follows. The one is the next module, which is imagine a pipe or pressure vessel, like a boiler, right? Let me just sketch this thing again. We've got a pipe, or in a heat exchanger, and there's some fluid in here, and that pressure will exert, the pressure of the fluid will exert stresses within the wall of that vessel. So pressure from fluids, right, is one other form of mechanical load. The other one is a change in temperature. So when we have a change in temperature, when it gets hot, something happens. When it cools down, something happens. Mr. Ntuli, I want to come straight to you, seeing that you work in a space with cables, and it's exactly a perfect thing. Mr. Ntuli, what happens when we have a cable and the temperature increases?
It tends to expand.
Does it really expand? Give us some experience, some real life experience. Give us a case study. Yeah.
If it hurts.
Yeah.
In terms of cable, it starts having losses.
There's losses as well. Yeah.
In the cable.
And obviously it starts to increase in length as well, right? You have to account for that when you are designing the cable. I don't know if is that true or not.
Yeah, because the material starts changing when it gets hot.
Yes. Right.
It structure.
Yeah. So we were talking about. We were saying, let's say there was a power line. Right. Just bear with my power line here. Transmission line, I think, is a better word. Mr. Ntuli can obviously is the expert in these things. And we have a cable.
Line.
Yeah. And if there's a change in temperature, this guy will extend a bit. In fact, when we're designing the structure, we must account for this change in temperature. That's one case I'm bringing up here. So that's another load. So when remember where there is a change in length, we get a strain, and therefore we get a stress, right? Okay, are we all happy with that? That understanding of what's going on here in terms of temperature. This is our core focus. I'm sure we've looked at the content before. You guys can say yes. I can't see your screen. Thank you, Mr. Ntuli.
Yes. Did you draw somewhere else now, so? Because I just see the question. I don't see drawing. Did you draw? Sorry, did you draw something?
I drew something here. It's not appearing?
Yeah, it's not displaying.
Okay, it's on the whiteboard. Can you see? Sorry about that. Thanks. I think that's open. You see now?
Yes, thank you.
Yeah, cool. So I was just explaining like the loads. There's a pressure load in terms of, fluid, water, air, maybe. And I'm talking about the change in temperature. And I'm just giving a quick illustration of, where this could possibly be a big factor. Okay. Let me just quickly undo all of this. We don't need that. All right. So reverting back to the stuff we're going to do, I'm just going to skim over some content for you regarding this some theory rather. Let me just open up my with the wrong place. So again, we have series connection and parallel connection, right? We're all familiar with that. And I want to bring something to you. It's just a lot of things, a lot of other theory, which I'm assuming you guys are actually going over, which I don't want to do all the Mickey Mouse examples, man. So, yeah. So when a material is in series, right? And I am being very, I am accelerating this process here. And I wanna take this, okay. So so if you have exactly the same arrangement, just to explain to you. Okay, so before I get here, do you recall when you're talking on the previous thing, right? Where we have something like this with another bar, that series, right? You apply a load here, and what happens here, right? Give me the formulas, the force, right? The total force is equal to Jason, Dalton.
It's
Yeah.
F1 plus F2.
Plus. That's
Yeah.
plus.
Not plus, they're equal to each other. Remember? Series.
Sorry.
Yeah.
Sorry.
Yeah. However, the change in length.
Change in length.
It's
we
plus.
add them, right?
Add them
Guys,
together.
black label's not good for the brain, eh? Okay. So then the next case would be we have some structure, let's just call it a pipe, and there's another structure inside here, right? Another element. And we apply a load, right? Compressive load, let's say. Tell me the force relationship here.
The total force
Yeah,
is component 1 plus component 2.
100%, right? Whereas the change in length, total change in length is?
The same.
Okay, they're equal. Yeah. So remember this, right? This is a separate loading condition. Because as Alton nice articulated to me via message, you figure it out that we are looking at two different types of loads. This will be one load, a mechanical load, and then we're going to be looking at a temperature load. And then what happens with both is that we need to find the resultant. So you're gonna see that in the parallel example we're going to do. So remember, there's two different loadings happening. One mechanical, right, which you know, and one temperature load. So now I'm going to explain to you the relationship. So the first thing I want to bring to you is the following. Let me just snip through this as well. This is for a series arrangement, right? For a series arrangement, just close these things here. It's distracting me. Let's have a look. Assuming that it's fixed on both ends, all right? They're typically fixed. Then what you have is that we have two bars like that fixed, and then we increase the temperature, right? Comes hot. So if we apply heat to steel, it starts to expand, right? I think we all can agree with that. So this guy will grow. This is what this is demonstrating. This guy grows. That guy grows, right? But now, as it's increasing in length, assuming that it's fixed, right? Because it's fixed, we have a resistance at the hole over here, okay? Like that and like that. So if you look at this arrangement, assuming that's increasing length, what's the nature or sense of stress induced in those bars? Would it be tensile or compressive?
Compressive.
Exactly, it's compressing because as it's extending, because it's fixed, it becomes compressed. Very important. And same time, as it's extending, right? The same force which is causing that compression is basically equal to each other. So the relationship for a series arrangement, force 1 is the same as force 2. And then in terms of the change in length, this formula over here, right, is is the temperature side, right? And this over here is the mechanical side. So they will experience a change in length, which will be of the same magnitude, but obviously there's the individual components. So this formula here works out the change in length due to temperature for each element, for each bar, and it's L alpha change in T, L plus change in T, and it'll equal the mechanical part. That's what it basically is. And then long story short, if you manipulate it, because the force is the same, you can take out F, you'll end up with that formula. This is for series, assuming that the temperature is increasing, right? If it's decreasing, there is a thing which you have to change by. The signs will change. I'm not sure if I can get there. So just remember this. I believe this is in your formula sheet, okay? So again, we're only dealing with the temperature situation right now. We're going to combine both. But remember that the force is the same. That force, which is going against the wall, is the same force compressing it, increasing that stress. Okay? I think we're on the same page here. So let's go to this example quickly. So here we have a compound bar, and it fits between that two supports. I don't know where we can see this in a real life setting. One on the left is steel, one on the right is brass. These are particular dimensions, and what happens is we have a change. What do you call it? A increase in temperature. Let me go red here. Hot. Of 65 degrees, right? And what they're asking now, what's the stress in the steel and the brass due to the increase in temperature? Okay, how do we begin? So we always start the same as the previous problems. We're going to say F1, 10.1. F1 equals F2, right? We know that stress, right? I just want to see something quickly. We can take stress ratios, or we can take ratios for okay, anyway, yeah. So that's the first thing, right? Then I'm going to go to the next equation. And the next equation will be that there. So it's going to be the change in length on the temperature side, which is 1, plus the change in length of the other side, which is 2, right? Okay, we know it as steel and brass. And that'll be equal to FLEA of the steel plus FLEA of the mergers of the brass. Okay, cool. So now we need to find F, and F is going to be the same for both, as we said, right? It's the same force inducing that thing. So now we need to find all the remaining stuff. Okay, so what do we have? So I do want to make you aware that this alpha is called your coefficient of linear expansion, right? I just want to show you a table. As you can see, I'm trying to teach you and solve these problems at the same time, so it's best if you go over. And different materials have different expansions, obviously, right? So I'm just going to put up a table here for you. So basically, the bigger the value, right, the more it will increase per degree. So if you increase it by 1 degree, then if you times with those other factors, you can actually get. So can you see steel has 12, aluminum has more, copper has more, brass has 19, wood doesn't increase that much, and glass doesn't increase that much. Okay. So Mr. Ntuli, can you agree that, I'm assuming you're dealing with steel and copper. I don't know, sometimes the cables have aluminum and copper. Can you see the expansion is a lot more? Is that true, or I don't know? Ntuli is not saying anything. But anyway, so each material has its own temperature. So what we're going to do first is calculate the total change in length on the temperature side, right? Which is the same as that side. So the length for the steel is 0.125. A coefficient is given here as 11 times 10 to the negative 6. And it's increased by 65. We must be careful. Sometimes in the questions, they'll say it increased from 20 to 50. Therefore, the increase is changing. The increase would be 30 degrees. Are you with me, colleagues?
Yes.
Because this is the change in temperatures. You know, yeah, it's just not the temperature, right? As you can see over there. Okay. And then our next length would be what is it? 0.2. Crosses are higher, that's 17. And we're timesing that by what's the other thing? The 65 as well. Okay. So guys, can you just get the change in length due to the temperature side quickly, right? Or X. Yeah, I'll change in length. Can I just get the total of this side here? I want to put it over here. You guys can work it out for me. And please try to work as fast as possible. No, it's difficult to ask that, but okay. Let me know when you got it.
Got 310.375 times 10 to the power
100%.
minus 6.
Yeah, there we go. So 310.375 times 10 to negative 6. Okay. So now we've got our total change in length, right? So now what we do on this side, because the force is the same, take it as a common factor. And this will be our unknown, right? So all we're left with is L over EA of steel plus L over EA of the brass over here. Okay. So I want you guys to find for me quickly this side. I believe you all can easily populate this, right? 200 for steel, 100 for elastic modulus, GPA. And then the area you obviously have to work out, which is pi over 4 d squared of each one. So this is for a series arrangement.
What did they say about the area?
The area is pi over 4 d squared. It's you know, I'm sure you know that, right?
I want to first calculate that then.
Yeah.
If we multiply d squared over 4.
We're going to find that force. And that force would be the same in both elements. Pause.
I'm getting 2.4757
Yeah.
times
2.4577. Okay.
4757
4757. Okay. Yes.
times 10 to the power minus 9.
9. Okay. So then it's a simple. You can check Jason's answer. It's a simple division issue here now. So we can find that force. What is that force? F1 or F2? We check. I get 125.404 kilonewtons. You guys agree with me?
I got the same answer.
100%. Okay. Jason, are you prepared for this next test?
Not as yet, no.
Okay. You sound very prepared.
I already covered this.
Okay.
Yeah.
So the parallel stuff is where you're biting your head on, you're knocking your head.
I'm at resultant stresses now.
Yeah, I'm talking about that then.
Yeah.
It's parallel. That's in the parallel side. I'm gonna do one of that. Okay. I don't know who else is in the house. I can see more people. Mzuki, Kwazi, you guys. I hope you guys are there.
Our F is 444.
125.44 kilonewtons.
125.4.
So guys, once you have a force, for us to find our stresses in each one is quite easy. Right? You're gonna take that force and divide it by what? The area, am I right? So that'll be the area of steel. And then just bear with me here. And that's the area of
Brass.
brass. Yeah. Obviously, just bear with me, I'm trying to cover enough ground. You guys can quickly compute that. What is important here, you put the sense as well with tensile compressor. Okay. I'll leave it to the house. Jason, is give them 2 minutes or 3 minutes, and then we can populate that. Alton, you winning?
I'm all right, sir. Thank you.
100%. Okay. So just wait 2 more minutes, and then we can yeah. Where are you?
You want the answers for that?
Sorry?
You want the answers for
Yes.
for
The stresses. Steel. Okay, Jason, give it to us. You're dragging the feet. Or Zuki.
It's 177 for steel.
100%.
177.4.
0.7. Yeah, 0.7.
It's 177.405.
Oh, okay. Fine. Megapascals. And is it compressed over tensile?
I think it's
Compressed.
compressed.
Yeah, it's been compressed as we talked about here. Exactly. It's very important. And the copper?
That's on there.
I'll put this here. It's also compressed as well. They've both been compressed. Remember, colleagues, we're only talking about the temperature load. I didn't put an additional load yet. That we're going to see in a parallel example.
I'm getting 99.443 MPa.
Okay, 99. Okay, I'm happy with this. All right. You're moving. So that's done for 10.1. We've calculated the stresses only, and I'll say it again, only for the temperature, all right? There's no external mechanical load. So the last one is the final distance of AB, right, from the right-hand support. So basically we want to see how much this thing actually extended by, right? So let's look at AB there. Oh, the final distance of AB from the right-hand support. The right is on the side here. So looking at this side and how much is that essentially push. So how that works is quite simple. Is that length, right? You take the original length, which you obviously have. We have to work on the original length because, yeah. And then remember, we had an original length, but at the same time, we had an increase due to temperature, right? You guys agree with me? You guys remember?
Mm.
So there's a length over here, all right? And then we apply the temperature increase, and so therefore it increased. Am I correct?
Yes, it's
Correct.
fun.
Yes. At the same time, when it increased, the hose restricted it, and so therefore it basically compressed. So original length increased due to temperature, and now we must subtract the mechanical part now. Okay, and you can do it from both sides. So how do we do this, right? If we're looking from the right-hand support, we're going to have to look at bros. So we know the original length in this case was, I believe, 0.2. That change in length is the same one you worked out over here of the temperature, but only of the bros, right? So the bros was this one over here. You see there? That piece here. What was it? 65 times it's 0.2 times 17. Yeah. Okay. And then this part is now the mechanical part. So we found that stress induced for this compression to happen, and that stress for the bros was the 99, right? 99.443. And what I'm using here, okay, so for this one, sorry, you can actually just use your FLAE. That's your mechanical extension, that one. So you take the force. There is a short way to do that, but anyway, I don't want to get into that. You take the force, 125.404. You times it by that length, 0.2, divided by the elastic modulus, which was 100. And then you're timing it by the area of the bros. And if you do this, you'll get how much it actually increased by. And what I'm telling you, you can do it either from the left hand or the right hand. But if you do it on the left hand, you're gonna have to use what is this one? Steel. Should get the same answer. Are you with me, colleagues? Temp, fixed or fixed compression. Yeah, at least we're half past now, so it's fine. We can move on to the next one. All right, are we happy with this? Let's just get that AB. It should be a very small distance. A very small increase. Temperature doesn't increase unless you're going really crazy with temperature. 65 is not too much. Point something over more. And what do we get?
I got for the total, I
Yeah,
got 41.443.
this.
Yeah. You will just check again, I think.
No, it shouldn't be. Shouldn't be. So I'll work out myself here quickly. 65 times 0.2 times 17. Was it 17 for the bros, eh?
Yeah.
Yeah, okay. So this guy should be 2 to 1 times 10 to the power negative 6. And this guy should be 1 to 5.44, if I'm correct there. 0.2, 100 times that area, and that area for the brass is, work that out. That should be 199.529 times 10 to the power negative 6.
I see my mistake here.
Yeah, so
I
basically,
used the,
yeah,
I used the stress relationship without, but I added the area as well.
yeah, I see. If you want this is the other way of, this is the same thing here. You see here? Same
Yeah.
thing. Yeah. I just keep it the FLEA for you guys because that's what you guys know. Well, this book is always like that. So Alton, what's my final answer there? So we can move on, guys, to the next question.
What's the value of E?
I got
Yes.
I got 200.021.
200.021 millimeters, no? Yeah.
Yeah.
So can we see? Oh, that temperature induced that amount of increase basically. Colleagues, is there any questions before I progress to the next question? The next one is going to help you in your test, and I'm sure definitely in the final exam.
So if for that X there,
Yes,
would you get the same thing if you use the stress times length over E? It's the same thing.
exactly the same thing. I can show it to you if you want. On a calculator if you want to see.
Yeah, because it's just
Okay, I
that
can show you. Yeah.
E is 100. That's why I got it wrong. 100.
So remember, you want to use the stress of the brass, no? Just the brass.
1.443.
Yeah. So then it'll be 99.443. I think my point is gone here.
Yeah.
Times.
I used the wrong modulus. The elasticity. What?
Yeah, you see? Yeah. You should get exactly the same answer. Can we move on, colleagues?
Yeah. Okay, it's fine.
Okay. Cool. So now, yeah, we only looked at the temperature, and now we're going to talk about this resultant stresses, or it's typical in a parallel arrangement. So what I recommend, the other papers, I have the other questions, and I want you guys to do the other questions. So I'm pulling up one from 2024 now. April 2024, the one I'm going to be sharing with you now. I just thought I will be efficient so you can actually see it's coming from a past paper instead of working. Yeah, okay. So now I'm gonna put that up. And yeah, you must be very sharp here, because I'll paste this here. There we go. So this is gonna be a parallel arrangement. So now I'm gonna give you an overview of what's happening here. Now, in this thing, the questions are typically asked, right? The first question, or sometimes they can switch it. We first only look at the temperature load. You understand? So what I mean by that is here we have a compound wall, right? Are you with me, Jason and Alton and Mr. Thuli?
Yes.
Luki? Yeah. So the first thing is we've got an increase in temperature. We've got to do an analysis there, right? Then we're going to find certain stresses in that guy and in that guy. In this case, we have a copper tube and a solid rod, right? Each one of them will carry its own sensors depending on what's happening, whether you're increasing or decreasing. I believe you're increasing here, right? So talk about that now. Subsequently, we then now apply a mechanical load. Right? You see? Now, when we do the mechanical load story, we must use these equations. You understand? Remember this? What you mentioned to me? And then we get other stresses now, which is going to be stress in copper and stress in steel, right? Can I make these other ones red? So you can see what I mean. No? Are you with me? So the first
Yes.
part is looking at the temperature section, getting that, and getting the sensors. And then coming to the mechanical part, which is 2.2, and we get that. Then in the end, we must now add the stresses of the steel and that one and that one. We have to add up, and we have to add this one and this one. So what you tend to find is that the sensors will be different, right? So remember, tensor will be positive, copper is negative. Are you getting the overview of what's happening? There's a temperature load, and then we're having a mechanical load, in this case, the actual tensile force, and then we're going to add the stresses together. Are we on the same page?
Yeah.
So, is everyone else on the same page?
Yes.
Cool. Kwazi and Mzuki,
Yes, sir. Following.
100%.
Following, yes, sir.
Okay. So let's begin. So now I'm going to talk about the parallel arrangement only for the stress, right? We already know the mechanical one. We did that in the last chapter. So how does this work now? So for a parallel one, I'm just going to pull the note. And just want to paste it here for you. So in this case, let me clear the whole canvas there. Here we have here's parallel. Two bars next to each other, not like the other one. And again, we're assuming that they are fixed. That's what's important here. Okay. So the first thing I want to tell you, right? They're saying here. So basically what's happening is that we have one bar like this and another bar like this. And these could be conductors, right? And they are fixed, I believe. They should be fixed. And what you find is that one bar will extend faster than the other bar. And that will be because due to the alpha, right? And what they say there is that when they get heated, they will expand. And they say because the two bars in equilibrium, the force acting on them is the same. So our relationship of force is the same. But then they say the tensile force that material one is experiencing, which is typically the one with a large expansion. In my case, it's the bottom, but it's on the top. Puts on material two, because they kind of join, I believe. And is equal to the compressor force. So the tensile force that material one puts on material two is equal to the compressor force that material two puts on material one. So what is important here is that you notice that one of these elements will experience a compressor force, whereas the other one will experience a tensile force, right? So looking at this proper sketch here, okay. I wonder if I have a better sketch, but okay, let me find this one. I want you to tell me in this case, what are the sensors? You guys admit that, student? Okay, cool. I'm gonna show you. This is from Trotsky, Strength of Materials for Technicians. Show you now. If you're unable to imagine what I'm talking about, maybe this will be better. I hope it will be. And if you want this book, just let me know. Don't think we're getting into trouble sharing this one. It's quite old. So like here we have a better illustration. So free expansion basically just means there's no restriction. But in this case, there's a restriction over here, right? The ends are blocked. So what I'm saying is, if it's fixed and we're allowed to expand, right? Can you tell me what stresses do you think is going to happen in the one in the middle, which in this case, the one in the middle has the longer alpha, the bigger alpha, where that is greater than the second one. So let's say this is copper on the inside and we have steel on the outside. So what stress would happen in the middle?
Compression.
Compression, exactly. And then what do you think is going to happen to the one on the outside? Look at this sketch here.
Tension.
Tension, exactly. This guy, I don't know what he's smoking, but we need to get on it quickly. That's the main aim here. So in the temperature side, when you find the stresses, right, you notice that the one with the longer alpha coefficient of linear expansion will get a compressive case in the case of a fixed case, and the other one will be tension, right? So again, if you want this text, yeah, I can always share it. So how do we do the thing for the other one? It's exactly the same as before. And for the temperature one, our forces are the same, right? Exactly as before. But now the difference is the change in lengths are different because one is increasing in length, one is decreasing in length. And then long story short, because in parallel, we assume the lengths are the same, and we basically work on this formula. And alpha 1 is the one with the bigger linear expansion, and alpha 2 would be the smaller one. So that's basically we're going to be working with over here. I hope that is clear. When it decreases, it kind of changes, but you guys are going to have to investigate that one. So let's try and solve the question quickly. I hope you're all on the same page. I really hope so. So let's look at this one. A compound bar consists of a steel rod, in that side, in this case, has a cross section of 500 millimeters squared, and a copper tube on the outside. And the steel rod fits rigidly, it fits inside. They're both 1.2 meters long. And yeah, the 2.1. The magnitude and nature of the stress, this is again tensile and compressive, in the copper and the steel if the temperature is increased from 30 to 95. Again, in this case, can you see, colleagues, that there's an increase of how much? Mr. Ntuli, can you please tell me?
65.
Exactly 65. I don't know what that was like. Yeah. So then, the same. We know that F1 and F2 is exactly the same. I'll just call this 2.1. And now we just go back to this formula now, yeah, right? Or this relationship will actually have formula telling us what's going on. So now it's going to be alpha 1 minus alpha 2 times change in T. The length is all negated because the length is exactly the same. So it is FLEA. Can you see the L's cancelled, because they're all the same length basically, right? And then we're basically left with F, open bracket, oops, and then it's one over this. Yeah, okay, just forgive me. 1 over 8. 1 over A, and this will be the, I guess, the copper or the steel doesn't really make a difference. All right, so it's a matter of populating now. So I'll just do the one side and I want to do the other side. So our linear coefficient of the expansions are 18 and 12. So this is 18 times 10 to negative 6. Then our change in temperature would be 65. You guys can get that for me. F is our only unknown. And we have 1 over the area of, what's this? Of steel. Right, so the area of steel, I can actually compute it for you. And it's going to be 500 millimeters squared. Therefore, that's going to be 500 times 10 to negative 6 times 200. Okay. Plus 1 over, what's the other one again? 900, right? The tube is 900. So that, and the, it's 105. Okay. It's 10 to the negative 6 as well. Okay.
On the coefficient side, I put 390 times 10 to the power minus 6.
Sorry, Mr. Ntuli. Oh, this is 210 here. Sorry, what were you saying?
I'm saying on the coefficient side, it's
It's negative
390.
6, sir. It's negative 6.
Yeah, I'm saying the answer is 390 times 10 to the
Oh,
power
sorry.
minus
Just give me a second. Thank you very much. Yeah, 390
90 times 10 to the
Like
power
this.
minus 6. Able.
100%. So you guys can solve for force for me. I'm not going to still do that part, so we can move along nicely. You know, you must sort out this, and we get the force. And once you find the force, find the stresses for me as well.
This
Can you
is
guys see my
para.
screen still? Okay. I'll give you guys 3 minutes for that. I just want to go to the toilet quickly. Two more minutes.
I can ask a question.
Definitely.
So is the length 1 meter or 1.2?
So I'll go back here. Was it alternate?
Yeah.
Okay. So if you recall what I mentioned to you over here, that the lengths cancel. You understand?
Okay, with you. Cool, no problem.
Yeah. So we're not actually concerned of the length because it's the same. Yeah. You can put the length if you want, but I mean, you know what I mean? Mathematically.
I'm with you.
always-
No, I'm with you. I'm with you. Cool.
100%. Perfect, man. Again, parallel arrangement.
Okay, right. Okay.
Okay, when you're ready, you can give me the answers. You need 1 more minute.
No, it's calculate that thing.
Yeah,
I'm
Mr.
getting,
Ntuli, you can see working hard. Okay, yes.
I'm getting 19.397. Yeah,
19.100%.
19.397 kilonewtons.
Okay, so once you're done with that, you find the stress in the steel. It's going to be this.
Oh boy.
What's the stress in steel again? I saw you the stress, the area there for steel was 500 times 10 to negative 6. And the stress in copper is 19.9397. And that's 900, no? So I want the magnitude and I want the nature. What do we get?
We're getting 21.552.
Perfect. Okay. Who is that?
It's Mr. That's
Okay, I took 1.552. Cool. For steel, no?
just for brass.
Oh, for copper, yeah.
Still,
What?
I'm still calculating.
Okay. Is that for copper?
Yeah, that's for the 900.
Okay, yeah.
Copper, yeah.
Okay. Now steel. And now steel.
I'm getting 38.794 MPAs.
Thank you, Chief. 38 point.
794.
Okay. So going back here, right? Can you guys recall the sensors? The copper was in the middle, right? This would be compressed, right?
Cool.
And this guy on the outside, which is the steel. Sorry. It's the other way around in this case. It's not like this. In this case, the copper was going ahead, no? So that means the copper will experience compressive and the steel will be tensile. You guys agree with that?
Yeah.
Yeah, perfect.
How do you determine that now?
Say again? How do we know?
Yeah, how do you determine the difference between the one which is getting compressed or
Like I said to you, so on the outside, no? If I'm using this sketch now like this, it's the inverse of this, Mr. Ntuli. So instead of the other one being faster, you know what I mean? It's not the inside, the outside is now going faster. Because this has a higher coefficient of expansion. How much was it again? What is it called now? What is it? 18, no? Because remember, this will grow faster in length. It'll go quick, and this one will be, what's it, 12? I'll explain to you now. Yeah, 12. So if it's, obviously I'm not sketching it all the way, that this would be compressed, assuming that it's now fixed now, which in this case it always is. And then this guy, yeah, this one here. And this guy would be in tension. You see? The reason why this is compressed because of this, that's the same as a series thing we discussed, remember? But normally in this case, it's always the one which grows faster, which is compressed, which has a higher or extends faster, the higher coefficient of linear expansion.
So the higher the coefficient determines whether it's getting compressed. So if it's higher, then that one they automatically gets compressed. If it's lower,
that is correct, yeah, because it will reach the wall first, basically, if I could say something like that.
Okay.
I know it's a bit, yeah. I normally when I teach this, I always do increase, decrease, and I do compression and tension. But I mean, yeah, you must conduct an investigation this weekend. All right. So what we've done now is only the temperature part now, right? And now we must come to Old Faithful, the stuff you did in module 2. And in this case, it's gonna be we have now, in addition to that, we have an axial tensile force of 60 kilonewton. Okay. See that? So now we must do what we did before in the other chapter. You remember in the test you did this. So in this case, at 2.2, F total is equal to F1 plus F2. You guys remember this? And therefore, that's going to be 60 kilonewton. Right? That's F1. And remember what we had to do is we look at what do we look at again? Is it the extension, right? Total is X1 equals that. And then normally we're going to say flea of the steel is equal to flea of the copper, right? Same extension. But the difference is you're going to get a ratio between the steel and the copper. Is it not so? You guys remember that?
Yes.
Yeah, so give me that ratio quickly. And in fact, you can eliminate the lens because it's the same length. So I'm gonna put, yeah. Jason, is this becoming a bit clearer in your eyes?
It's only the last part where you actually get the
Don't worry.
resultant. Yeah.
You have the best here. But let's get that ratio first. This is the mechanical part now. Okay.
I got F of the copper is equal to 0.9 of the steel.
So F of the copper is 0 like this, like that.
Other way around.
This way.
Yeah.
Okay. Perfect. I believe he's correct. I trust him. So we take this guy and we substitute it in over here, right? Kawazi, are you there? Zuki following. So this stays the same. Plus now we have F of S 0.9. And all we must do now is do a quick math story over here. I'm assuming that is correct. And we can find the force of steel. And can we quickly do that?
Just want to double check, is it 60 kilonewtons or 65?
No stress. You'll check now. It's 60, sir. Thank you.
Okay.
Yeah, thank you very much. You're smoking the good stuff, guys.
Yeah.
Eliminate that. 60. Okay. Thank you. Times 10. I'll wait on the answer from you guys. Are you sure it's 0.9?
I can double check, but yeah,
Yeah,
I'll work with
just remember the modulus of elasticity is not 200, no? It's 210 and 105.
Yeah.
Yeah, just check that, guys. Check the ratio. I don't think it's correct. Check this ratio. I'll wait on the other colleagues to check for us. So E here is 200 and I can bring it down for you. Just give me that ratio. Make sure you get the ratio right.
Okay. This is 500. That's good.
Yeah, I checked again, I get 0.9. But the other way around, it should be 1.11.
Let me just double check here
Yeah.
because I'm seeing something else. Let me just confirm something. No, I think you're correct. I think you're correct. I think you're correct. You're correct. But I'm realizing there might be another. I see I see what the issue is. Yeah, I think you're definitely right. Yeah.
Okay.
Yeah. No. Wait.
I'm
No,
getting
it
one.
can't be. It can't be. It should be
I'm
2
getting
or half.
1.111.
Are we not getting?
I'm getting
Um,
1.111.
Mr.
Okay,
Matthew,
my
can you,
bad.
can you go up
It's
so that we
fine.
can confirm the numbers?
No. I think you guys are right. Sorry, my bad. So 0.9. No, it's fine. It's fine. So what is my force in steel? Sorry about that, man. I think my anger was kicking in. So my force in steel should be. Sorry about that, guys. 31.58 kilonewton. Are we happy with this?
Sure.
And therefore, our
Yes.
force in copper must be 0.9. Should be 35. No. What am I talking? Yeah, 35. 35?
28.42.
Yeah, 28.4. Sorry. 28. And the angle is kicking in. Okay. So once we have that, we then have to compute the stress as we did before. So 31.58 kilonewton. And we divide that by the area of steel, which was 500. And then we must do the copper with that respective. Okay, let's quickly get that stresses. So what is my stresses?
For copper, I'm getting 31.579 megapixel.
31.979.
579.
And then for our steel,
I get
That's fine.
63.
yeah,
I get 63.152 or 158
158. Okay.
megapascal.
Is it 31.979 or did I miss something there?
579.
579. So I thought, yeah. Cool. And our colleagues, because this was what is the sense of this force? Do you guys remember on the mechanical side? What are the sense of the stresses? What's the sense of the stresses?
Compression.
No, mechanical. Tensile. Tensile stress was induced.
Tensile,
You
sorry, you're
understand?
right. Yes.
Right, though. Okay. Are we happy with this? You're playing with the big boys now. Let me do it like this. Okay. So what you can do now for your table, like this. Stress of steel and copper. And here we put just want to remove this. Can you just mute your mic, Chief? I was talking. And here we can put temperature load, and here we can put load. What can I call this? So a mechanical load, no? You can call it something else, but I'm just and then over here we have the resultant over here at the bottom, resultant stress. Okay, it's quite simple. So let's go back to our loads on the temperature side. And we saw that the steel had a 38.794 tension, right? And that was a plus, right? Because it's in tension. We then go to our copper load on the temperature side. It is 21.552. Are we happy? And that's a negative because it's compression. You guys agree with me?
Yeah.
100% right? Then on the mechanical side, we had for the tensile load, I should rather say. For the steel, we had a 66.158. And here on the copper side, we had what? A 31.579 positive. Are we happy? Does that make sense to you?
I'm
Colleagues,
still
does it make
lost,
sense to you?
but I'll catch up.
Okay. Who's that? Listen to again.
Uh-oh.
Oh, okay. Who's that? Quasi. Quasi. Okay. So again, remember the question was asking for the resultant stresses, right? So we're first checking now for the temperature, right? And then we put those stresses in this table there, right? Okay. 38 and the negative. Then we look at the mechanical ones we just worked out now. And it's over there. All we have to do for the resultant stresses in the steel, we have to add them up, right? So we add this and we add that. So what happens when we add these two here? So the resultant stress in the steel is simply going to be plus 38.794 plus 66.158. You get our answer. Obviously, this is in MPa, right? You guys happy? Okay, so I hope you're following this.
Yes.
Yeah, and then we do exactly the same for the copper, but the copper in this case, it's minus 21.552 plus the 31.579 MPa. So we're just adding. So here we add plus, right? So what do we get there?
104.952.
104.952. So remember,
Yes.
because it's positive, therefore it's going to be tensile, right? Are you with me?
Yes.
Because the last one is positive, and the bottom one, so it's minus 21.552 plus 35.579.
It's 10.021.
10.021.
021.
Is it positive or negative?
Positive.
It's positive.
So therefore it's tensile. Done. And we've completed the question. Welcome to N5 Standard Materials and Structures, guys. How was that?
Oi.
No comment. Mr. Ndul is thinking, why did I start the subject, huh? Quasi, you good there? Now, I'm in over on this note, because we're at the end. And guys, make sure you know the parallel arrangement for the next up and coming test, right? I'm not going to say that again. If this load now, if they said now, instead of an axial tensile force, it was an axial compressive force, right? These sensors over here will change to compressive. You understand? Right? Then therefore, that this part will be negative and that will be negative. And then when you add them up, it'll give you a different result. Are you with me?
Yes.
Yeah, so that's very important, knowing the sensors of the load. So I'm gonna show you one question where it's in the questions I sent. You know what I recommend you guys solve it and put the answers in the group. And where is this now? I'll paste it over here. Here you go. So can you see this one? Same type of question. Yeah, there's an 80-degree increase, and this one a compressive load of 25. Can you see now? But
Yes.
the same story. Yeah. So try this one and then put the answers in the group and we can all compare together. But colleagues, thank you very much. Hope you guys learned something. Yeah. So check, look at this, Mr. Dooley. You can show your family what you've done here. Show your son and your daughter. It's a lot of work, guys. Okay. I'll see you next week, eh? We do module 7. Toasting of shafts.
All right. Will
Cheers, guys.
Mr.
Yes.
Kulubela send the recordings for the ease of reference?
I send the recordings, Chief.
Okay. Would
Yeah,
you
so
read?
just remind me tomorrow morning.
Thank you.
Okay. And I can even post
Thank you,
the
sir.
other last year session as well. Yeah. I had a question. Was it Jason or Alton or? Okay, guys, I'll see you, eh?
Okay, thank you, sir. Thank you, sir. Sorry.